Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we were discussing about the form of drag force, and now in this module I will try to highlight which form is necessary at what point of time or what values of the dimensionless group Re. So it turns out that the form 1 involving the function f may be used for large velocities. Large velocities, again this information is coming from the physics of the problem or the fluid mechanics of the problem. And the form number 4 is written can be found using small velocities, right? So this question is how to find g of Re, the function. How to find certain experiments have been done in fluid mechanics where it has been shown that this function behaves as follows. So I am just trying to plot some experimental results. If we were to plot g of Re versus Re on the log scale, so let us say 10 to the power minus 2 to 10 to the power 0. So this is on a log scale. So log of g of Re by log scale. So this is a log scale plot, and we see that there is typically there is a linearly decaying relation on the log scale of g of Re versus Re, right? So which means that this function decays with increasing Re. So so it turns out particularly it is very important for people working in this area of fluid mechanics to know what is this function g of Re for small values of Re or low Reynolds number. The Re is denoted by the group of the so-called Reynolds number. Re is the Reynolds number, right? So of particular interest is the dependence of G for small re. So it implies that small re implies small v. Small re implies small v, and we call this type of a flow as the so-called Stokes flow. Okay. And we have seen that from the experiments, typically g is a decreasing function of Re on the log scale. So typically from experiments we find that log of g, log to the base 10 g, is a minus b log Re, right? Or we find that g is alpha by Re to the power b, beta, where my alpha and beta are related to a and b as follows. For example, alpha is 10 to the power a, and similarly beta is 10 to the power b. So this is on the log scale. So then further experiments have shown that if we do a curve fitting, then this alpha comes out to be roughly 6 pi, which is roughly 17.6, and beta roughly comes out to be 1. So the conclusion is from here, from all this observation, the conclusion is that for small values of this Reynolds number Re, the drag force comes out to be 6 pi mu r by v, right? So this is a very famous formula for a motion, for a drag of a falling spherical object when the velocity of the falling object is very low, right? So this is what it is. So then this question typically people ask is, how do we know that the drag depends on the radius, the viscosity, and the density and the velocity? Why not some other parameters like temperature or so on and so forth? The answer to this question lies with the fact that we need to have a little bit of understanding about the fluid mechanics of the problem, right? So this question is, how do we know to assume that the drag depends on the radius, the velocity, the density, and the dynamic viscosity. So the answer to this lies on the fact that we need to have a knowledge about the laws of fluid mechanics. So knowledge of fluid mechanics, right? And this will lead to the corresponding parameters for drag. Okay. So then we will try and focus on another example. The example is that of the motion of toppling dominoes. So what exactly is this? So this is the case of toppling dominoes. Right? So what are we getting? So dominoes are typically blocks of objects which are kept one after the other, and if we were to push one object, it is going to fall on the other object, and this motion is going to start to repeat, and we will get a nice pattern when the domino starts to fall, right? So typically we will have this new motion where this domino starts to fall here, and the dominoes are going to fall, right? And we expect that this is the motion that occurs in this direction of the falling dominoes. So now, in order to determine the motion of these dominoes, let us now assume the height of these objects as h and the width of these objects as w, and let us say the width d of these objects as the distance between the various dominoes as d. So in domino toppling, domino toppling is the art of setting and knocking down the dominoes. So domino toppling, art of setting dominoes and knocking them down. So we assume that the velocity is v. It depends on the spacing d. The velocity of the domino toppling is v, depends on the spacing d, and it also depends on the height h, it is, and as well as the thickness w, and the gravity g. So again, coming from the essential physics of the problem. So velocity of the domino, spacing between the dominoes, the height, the thickness, and so on, and the acceleration due to gravity of the falling masses. So again, we can do a fundamental dimensional analysis. So we are assuming that the velocity of the falling dominoes is a function of the spacing d, the height h, the width w, and g, or we have the dimension of v depends on d of a times h of b times w of c times g of e. And now if we were to do a fundamental analysis, we see that Lt minus 1, which is the dimension of velocity, is equal to L of a plus b plus c plus e times t of minus 2e, and e comes out to be 1/2. B comes out to be, notice that we can only set up two equations, one for L power of L, one for power of t, but we have four unknowns. So of course we will have two dimensionless groups, pi 1 and pi 2, right? So we expect that B is 1/2 minus A minus C, and that is all we can find Now the velocity v is alpha times d of a, h of 1 by 2 minus a minus c, and w of c times g of half. And now what we get is that the velocity is alpha times square root hg times d over h to the power a times w over h to the power c. And these are my two dimensionless groups, pi 1 and pi 2. And we see that so that is what we have, pi 1 and pi 2. So we see that v is square root hg f of pi 1 and pi 2. So this is the most general functional form of pi 1 and pi 2. This is again, the idea is similar to the previous example. Idea similar to case study 2, right? And where f is an arbitrary function. Okay, so then this question is how to really obtain this general solution in this case when we have more than one dimensionless groups. So this question is how to obtain general solution when more than one dimensionless group, one dimensionless product is involved. So we can do a little bit of simplification in our problem. We can first assume that the dominoes are thin. So these are thin sheets which are falling on top of each other. So dominoes are thin, are very thin. So which means that the width of the dominoes is much less than the height of the dominoes, or the second group pi 2, which is width over height, this is equal to 0. If that is the case, then we expect that the domino velocity will be square root g times h times g of pi 1, because pi 2 is assumed to be 0. And then we have seen, so what has been seen experimentally for these domino experiments is typically through experiments or experimentally, this value of g comes out to be a constant which is 1.5. So the domino velocity comes out to be 1. Again, this g function, this is found experimentally. So I'm just giving you the experimental values which are observed. So typically this is 1.5 times square root gh, right? So again, the moral of the discussion here is that most of the time the dimensional reduction will give us the answer to the problem up to an unknown constant or an unknown function of a dimensionless group. The rest has to be found through experiments. That is the constant or the dimensionless group, right? So but the simplicity of this dimensional analysis cannot be ignored. That is what I'm trying to highlight here, right? So now with all these different case studies, let us try to establish the theoretical foundation of dimensional analysis, the so-called Buckingham pi theorem. So we are trying to establish the theory of dimensional analysis using the so-called Buckingham pi theory, the Buckingham pi theory, right? So suppose the physical quantity, suppose the quantity q depends on the variable. Suppose the quantity q depends on the variable p1, p2, pn, and suppose we have that each variable pi's, these pi's can be expressed as in the form of the fundamental dimensions L, T and M, right? So we can, so I'm not writing this statement, so which means that the fundamental dimension of Q is going to be L times L naught, T times T naught, M times M naught, right? So that is the dimension of Q, and the dimension of PIs, which is the representing variables, these PIs, they have the fundamental dimensions as L times Li, T times Ti and M times Mi. And now we can assume that Q is has a functional dependence, has some form of functional dependence on PIs, and which means that we can now write down the dimensional analysis of Q on dependence on Pi as follows. So this is equal to P1 times A1, P2 times A2, Pn times An. Or now we equate the dimensions of L. So this is L1 A1 plus and so on Ln An, which is L naught, and then we have T, which is T1 A1 plus and so on to Tn An, which is T naught, and M, which is M1 A1 plus up to Mn An. So we have set up the three equations here corresponding to the fundamental dimensions L, T and M. We see that we have got a matrix. This is a matrix vector equation set of total number of equations having just 3, but number of unknowns being n, right? So we have 3n, sorry. We have equations 3n where the unknowns are 3n, where the unknowns are the Li's and the Ti's and the Mi's. Okay, so now in the matrix vector form, what we see is that we can write down, well, the unknowns are not Li, Ti and Mi, the unknowns are A. The vector A, the A's are these Ai's. We want to find these Ai's. So these are my unknowns. Okay. So A times A is equal to B, and we see that my matrix A is L1, T1, M1 and so on. So Ln, Tn, Mn, and the vector small a is A1, A2 up to An, and the vector B is our set of 3 3 cross 1 vector for B, which is L naught, T naught, M naught. So that is the power of the dimension of Q. So we see that in this setup we could have only two cases. We could either have, for this, let me call this equation set 1. So equation set 1 has only two cases. Either we will have infinitely many solutions, which means that we will have either more than one solution, which means that we will have at least one or more than one dimensionless groups, or we will have no solutions, which means that the equation cannot be found, the dimensional analysis cannot be done. We will certainly not have a unique solution to the problem, and which comes slowly allows us to allows us to come to the real statement of the Buckingham pi theorem. Okay, so suppose we look at the first case. So suppose one has no solution, has no solution. So this is simpler because we know that in this case dimensional analysis cannot be done. So so in this case we have assumed the assumption that Q depends on P1, P2, Pn is incomplete, and we need additional parameters. to complete the system. So now, which has brought us to the fact that we need to define what do we mean by dimensionally complete system. So let us now introduce the definition. Dimensionally complete system. So the set P1, P2, Pn is dimensionally complete for Q if it is possible, dimensionally complete for Q if it is possible to combine PIs to get a quantity with the same dimension as that of Q. To get a quantity with the same dimension as that of Q, right? So which means that at least the system can be solved, that is, we have a solution, then we know that the system is dimensionally complete. Now suppose if we assume that PIs are dimensionally complete, so assuming that the system can be solved, PIs are complete, then what happens? Which means that there exists at least one solution. There exists at least one solution of 1, right? So let us say now we introduce, so at least one solution implying that we could have more than one solution, so at least one solution, right? Which means that again, coming back to the idea of linear algebra, we could introduce the concept of null space and the codimension space. So let us say we introduce, let A1, A2, AK be the basis of the null space, of A, right? So we have that n of A is the, we denote in linear algebra, we denote by the null space as this curly n. So n of A is all such vectors A such that the matrix vector multiplication gives us 0, right? So then what we have is that the general, in this case the general solution of 1, this is again from the standard result in linear algebra, the general solution of the system 1, the system which is the dimensionally of our dimensionally complete system. So the general solution of 1 will be A will be equal to A particular plus summation gamma times AI's. AI's I is from 1 to some k. So A particular will give us the particular solution to the non-homogeneous equation, and and AI's gamma i's will give us all the combinations of the dimensional groups, the non-dimensional groups. So this will give us the non-dimensional groups, right? This null space. So let us try to see this example by going back to observe the case of the drag of a sphere, right? So example, we are revisiting the case of the drag on sphere, right? So what we see is, for a drag on a sphere, we go back to look at the equations equating the length, the time and the mass, and we see the following matrix vector formulation. We see that this, for length it is 1 1 minus 3 minus 1 times A, and then 0 minus 1 0 minus 1. Again, if we go back to the drag on a sphere, I think a few slides back we had drag on a sphere somewhere here, drag on a sphere, projectile drag, where do we have here, drag on a sphere. and we saw that this was the equation I'm talking about. So for L it is 1 1 minus 3 minus 1, and on the right hand side it is 1. So that is what I'm writing here. It is 1 1 minus 3 minus 1, and on the right hand side it is 1, right? And similarly for the other sets we can write B times minus 2, and the rest is 0 0 1 1 C times this is 1, right? And then we will actually have, this is a 3 cross 4 matrix, so we will have a fourth unknown which is D, and from here we can do a row reduced echelon form of this matrix. We see that, so this is row reduced echelon form. We see that the new matrix comes out to be 1 0 0 1 and 0 1 0 1 and 0 0 1 1, and this is going to be the right hand side is 2 2 1, and we see that A comes out to be 2 minus D, B comes out to be 2 minus D, and C comes out to be 1 minus D. And from here I can find that my solution A B C D comes out to be 2 2 1 0 plus gamma times, again with this D is minus 1 minus 1 minus 1 1. So this is the coefficient multiplying D here, minus 1 minus 1 minus 1 and D being 1. So here is the particular solution for the vector A. That is the particular solution I was talking, and I have found that there is one dimensionless group. So the null space is having one vector which is minus 1 minus 1 minus 1 1. So that is my null space, and that is what was I talking few minutes back. So then we are ready to, so let us now generalize this result, and let us then state the Buckingham pi theorem. So generalize, let us say, let the ith basis vector is AI. So this is alpha, beta, and so on, gamma. This corresponds to the following non-dimensional group. This corresponds to the non-dimensional group where pi I is P1 alpha, P2 beta, and so on, Pn gamma. And we see that the AIs are independent. So the null space, the vectors are independent. So since these AIs are independent, we expect that we will have the independent dimensionless groups pi 1, pi 2, and so on, pi k. They are independent, right? And now we have, let us say, our particular solution AP is A, B, C, and so on. And so now what we have is that our variable Q will have the dimensions which is P1A, P2B, and so on for these variables P1, P2, Pn, right? And this has the same dimension as my original variables small q, right? And then what we expect now is that the variable small q is alpha times capital Q. This is coming from the particular solution, times the groups which is pi 1 k1, pi 2 k2 times pi n kn, right? And where my constants alpha and ki's, these are constants. Okay, so what we have found is that if the system is dimensionally complete, we can find the formula for the variable in the form of these dimensionless groups, and which brings us to the Buckingham pi theorem, which we will state formally in the next module. So thank you so far for listening.